Hello and assalamu alaikum everyone. My name is Moaz and a partner with me, Anas. We're going to be presenting the idea of a research paper which is towards evaluating the robustness of neural networks. The basic idea is that deep learning is being used everywhere in today's world, from self-driving cars to facial recognition. But it has a weakness. Tiny changes in the input images can cause models to make wrong decisions. These are adversarial attacks. Understanding and testing these attacks helps us build safer AI systems. So, moving on to the motivation. So the motivation is that even the best models can be fooled by small invisible changes. This can be dangerous in real world applications like medical diagnosis or autonomous vehicles. Some defenses try to stop these attacks, but we need to test how strong these defenses really are. That's why we focus on powerful attacks and try to design something to bypass them. Then comes our problem statement. The problem statement is that many simple attacks fail when models techniques use defensive distillation. We aim to use the Carlini and Wagner L2 attack, which is a smarter type of attack, which is optimization based, that can still fool protected models. Our goal is to implement it, run it on ImageNet, and evaluate how well it works. Coming to our related work and our approach. So the related work we can see is we have seen defensive distillation being used. We have also seen success rate of being very high for protection, and also we know deep fool and JSMA are also some types of uh, defensive approaches which have been good for an effective scale. Our approach is using a loss function which is modeling logits. The Inception V3 model is being used. The ImageNet dataset is being used, and the PyTorch 2.5.1 is being used, which is which we can say is the latest model of PyTorch. We've seen a lot of previous ones as well, but all of them were the versions which were using PyTorch 1 or PyTorch previous versions, but not these ones. Coming on to our proposed solution. So the proposed solution we have is that the authors have designed three main attacks, of which we were using the L2 attack for our idea, which Anas will be presenting ahead. We have in the research paper L0, L2, and L infinity attack, in which three attacks are trying to break down that network and try to uh, break the distilled networks and trying to get a false result out of them. Here we see two images where a true label is given out by a giant panda, and there is a small change in that image which causes it to give a false result. Next, ahead, our Anas will tell you about other parts of the.
Okay, so moving on to our actual implementation. So as Moz mentioned, we had implemented the L2 attack for the research paper. And basically, to give an overview of the L2 attack, it is an optimization problem. We have a loss function, and we have to optimize a formula, which I will discuss later. So, and a basic summary is we have to find an input to find an adversarial image which just looks like an original image, which, as I showed in the last slides, the two images look similar, but they have a very small change that will enable uh, the model to misclassify. Also, to what is a small change that is being found out by L2 distance, which is Euclidean distance, and to find the minima of the distance, we are using Adam optimizer. And moving on, so this is a function that was proposed in the paper that we are discussing, which is 1 upon 2 10 h of w, which is the image. And basically it is uh, casting the image into 10h subspace and finding the sorry, it is finding the difference in the original image, where x is the original image and 10w is the the type, the casted image, and we are finding the squared distance. So basically we are finding the the squared distance, mean squared distance between the image. Okay, so the complexity of the total code depends on three things: the maximum iterations that we are using to attack the model, the batch size, and the sum of the forward parts of the model and the backward pass of the model. So what is forward pass? It is basically when the model tries to attack, and when we are using the optimizer or the loss function, it is using gradient descent to using backward pass to find how to optimize and minimize the distance and get better predictions. Okay, however, there's a trade-off. When we are trying to optimize a model, it takes more time to load. Okay, so the experimental setup, as Moz had mentioned, we are using ImageNet dataset. We have also tried on CFAR and MNIST datasets, and we are using a pre-trained Google ImageNet version 3 of the model. And these are some metrics that we were using. So C is a constant. The greater the value of the C, the higher the, or the more stronger the attack would be. The kappa is basically the confidence that the model will have, the maximum iterations, and learning rate. So learning rate is pretty large, and even then 0.01 is larger in terms of CNNs, and even then the model was working very fine. And before the demo, I just wanted to discuss the results. So the true label was initially giant panda, so this means the model was predicting the right results. But after the adversarial attack with the L2 distance of 53.5, the model was predicting a different. So so this time it was predicting space shuttle when I ran it. And on even the models trained using using distillation were were being tricked to misclassify the image. So let's now begin with the demo. Okay, Moaz, tell me if the Google Colab is visible to you. Yeah,
Yes.
okay. Let's begin. Okay, so this is a basic code in which I am loading my data set, which is the ImageNet data set. And so we are using, yeah. So this is a sample image of a giant panda with the true label, and the model was predicting the image correctly. So, yeah. So images. So model was pretty, yeah, here's a model. So I was loading the model, and after, and these are the equations that I was using. So minimize the distance, the squared distance, mean squared distance that we are using. And this is the main function of L2 attack. So first, as the model requires the images to be in certain pixels that we have already set above. Yeah, we have shaped the tensors as per the requirement of the image v3 model. After that, we are using the Adam optimizer, as we mentioned. And to create adversarial image, here I am calculating the mean squared loss, and squared loss basically iterates to some steps. And as soon as, if it finds the adversarial image that the model is misclassifying, then we are breaking to avoid additional computations. And after I run this model on the, yeah, so after I ran this model, the model was able, before finishing the steps to define a model, was able to find an adversarial example. And this was an adversarial example that just by distorting some amount of pixel, the model was being tricked to classify it as a space shuttle. However, clearly it feels like a panda. And after that, okay, so I had also plotted a chart. Okay, so GradCam chart basically focusing on, so what after on the adversarial example model was focusing on, that it was being predicted. So this was the part. So one is basically the part the model focused on, and due to which it was tricked to classify it as an adversarial example. Yeah, so continuing the presentation now, let's jump into the conclusions. Yeah, so let's discuss the limitations of our current approach. First of all, due to it is working on CNNs, it is computationally not really computationally expensive. However, if we increase the data set, the batch size, it becomes computationally expensive. And so another thing, as we are assuming it is a white box approach, that we have all the control over the model, we know how the code works. However, it would be difficult to find an adversarial example for advanced models in which the attacker doesn't has access to. For example, Clip and GPT Clip model, it is hosted on their servers. And for the future work, we intend to complete the paper by implementing the L1 and L infinity attacks as well. And okay, so this was pretty much it. And there are many defensive distillation examples as well, which are being found out on the internet. Yeah. Thank you so much.